All right, so thin film, so we're going to define a thin film as a thin layer that we'll place on some other substrate. Okay, so let's say, for example, we're going to put a coating on top of, I don't know, water, maybe. That's kind of what you did yesterday with your, with the nail polish. So let's say this is H2O. Let's say the index of H2O is 1. Let's say this is some coating here, or thin film. We'll use the words coating and thin films interchangeably. So let's say the index for that is, how about 1.5? And then of course out here we're going to have air. So here's what happens when we send light into this. Let's say we send a beam of light this way. Light's going to hit the coating and it's going to do two things, right? What's it going to do? Okay, some of it's going to refract, okay, and some of it's going to reflect. And then when this beam comes down here, what's it going to do? Some of it's going to refract and some of it's going to reflect. And so forth and so on. There'll be continual reflections happening. But what we care about here is these two. So these two reflections. Because when these two come back together, let's say this is your eye right here. When these two beams, let's call this beam 1 and beam 2. When these two come back together, beam 1 and beam 2 do not travel the same distance, right? Which one travels farther? Beam 2. Okay? So beam 2 and beam 1 are going to be out of sync with each other, or possibly out of sync with each other. If beam 1 and beam 2 were exactly, say, 1/2 of a wavelength, so let's say the path difference, I'm just going to use delta L for this. Let's say the difference in distances that they travel, the delta L, was exactly 1/2 a wavelength. What would you expect to happen when these two beams come back together? You'd have one wave that travels, say, this distance, one wave that travels a little bit farther. What should happen when they come back together? They should destroy, right? So this should be destructive interference in this case. Okay? Meaning, if this one traveled exactly 1/2 of a wavelength farther than this one, what would you see when it reached your eye? You should see nothing. Yeah, you shouldn't see anything because they would just completely cancel each other out, right? So if this was a red laser, for example, it would completely cancel out here. Okay? What if this were, say, white light, and the red happens to travel a little bit farther? Would it still look white to you? If the red cancels out, then you would see, well, you wouldn't see Roy G. Biv, you'd see Oi G. Biv, right? And the red would be missing, and your brain's interpretation would be different, right? So you wouldn't necessarily see that. So this would be an example of destructive. Now, what if this laser instead had a path length of, say, 1 wavelength? What would happen with that? Then this would now produce constructive, right? So you'd have wave, and then this one would go 1 wavelength farther. When they came back together, this would be constructive interference. Okay? So in this case, if you sent a red laser in, what would you expect to see? You would expect to see a really bright red. And if you sent the white in, what would you expect to see? Red would be emphasized because this would be like double the brightness, right? So that red color would be emphasized. Okay, so that's kind of the whole concept of what you did yesterday. And depending on the thickness, so when you had your little bubbles, what's going on with the thicknesses? Was it a nice constant thickness like this? No. Okay, what was happening? Okay, it was changing, the bubble was moving, gravity was changing it, and you probably saw a shimmer almost when you were looking at it because of that constant motion, that constant change in the wavelength. And depending on what was being constructed or destructed, that would create the different various colors that you might have seen. Okay, so that's kind of the basic concept. Notice here, so this one I have it at an angle. So if I change the angle, what should then happen to the path difference? If we came in at a steeper angle here, what happens to the length of that second one that's traveling? It's increasing, right? So you're changing that angle. So if you looked at it at different angles as well, you should have saw different colors, spectrums, depending on what angle you were actually looking at. Okay? So the purpose of simplicity, we're going to assume that this is going to just come straight down when we do our calculations here, straight down like this, and then straight back up. In that case, if this is the thickness, let's call this thickness T, if this is the thickness, then how much farther is that second beam traveling compared to the first? Twice T, right? It's traveling exactly twice the thickness, because that's go down and back up, as the first beam.
Can you say that again, please?
So if this is beam 1, I should probably be using different colors, but if this is beam 1, here the pink one, and then beam 2, let's use blue. Beam 2 is going down and then back up, and then when it comes back up again, they come back together. So beam 2 has to travel T down, T back up. So it travels exactly twice the thickness of this coating compared to beam number 1. Okay? So if twice the thickness of that coating is exactly equal to a half of a wavelength, what kind of interference should you expect? Destructive. And if twice that thickness is one wavelength, what should you expect? Destructive. Are there any other of these that we could do? What else would provide destructive interference? 3 halves, 5 halves, etc. Right? So any of those half multiples. Same thing with this. Any whole multiple, L, lambda, 2 lambda, 3 lambda.